Welcome everyone, we're ready to start. The topic today is the IP layer. Last week we went through it very quickly. Today and next week we will go through some of the more details. The IP layer, as illustrated by this figure, is the global interconnection. So this is showing some of the cables that interconnect the actors in the backbone of the internet. The IP layer is based on a very small number of principles. The first one is that it uses addresses, of course, and in routers, in forwarding system, it uses longest prefix match. So this is illustrated on the next figure. Here I'm showing hosts like this one, this machine, that is talking to this or to that machine, and it is showing a small part of the internet with 4 routers. Inside the routers, there are tables, forwarding tables, that are usually called routing tables. We zoom on the table of router R2. We see the table contains things like destination address prefixes and where it should go. Where it should go is normally the name of an interface and also the name of the next hop. We will see that in the lab. Here I'm just showing the name of the interface, and we see the star means anything. We'll see that the convention used on the internet is not to use a star. We will see the notation that is used in a few minutes. Right now, star means anything. So here it means any address that starts with A, capital A. Capital A is a block of bits. Depending on whether it's IPv4 or IPv6, we'll have different notation. It means a prefix, part of an address here. Anything that starts with A should go to output 1. Anything that starts with B should go to output 3. And anything that starts with B.D should go to output number 2. We see that there are overlapping entries in the table, because if something starts with B.D. something, like this destination address here, if Lisa sends a packet to Bart, this packet destination address matches 2 lines in the table, the third and the second one. When you match 2 lines, we take the more specific one. This is what we call longest prefix match. So here, the third one is ignored. We take this one and we go to number 2 here. If Lisa sends a packet to Homer there is the address B.C, so the only match that is true in the table is the third one, so it goes to output port number 3. This is how the internet is organized. This is how the routing tables in the internet are organized. The beauty of longest prefix match is that it allows you to aggregate a large number of things. For example, we see that in router R1, anything that starts with B is going to port number 2, so there's only 1 line for a large network, perhaps B, or a large fraction of the world. Also, we can do things by default. Here, we can interpret the routing table at router 2 by saying, by default, any B goes to 3, except an exception here, that is number 2, that goes to B.D. So we can have defaults and exceptions by combining different prefixes and this longest prefix match. The second principle that governs how the internet works is that we don't use routers inside a LAN. A LAN is a local area network. A synonym for IP is a subnetwork. If I have here 2 machines, like B and E, that are talking together, if they are on the same Wi-Fi base station, on the same local area network, there's no reason to go through a router because they can communicate directly at the MAC layer. So if you can do without IP, you do without IP. Or more precisely, if you can do without routers, you do without routers. So that looks obvious, but that's a principle to remember. Similarly here, if W sends something to the printer, it will not go through the router. But of course, if W sends a message to E, it will have to go through the routers because they are not on the same LAN. If we apply this principle to this small example, what destination address will we see here? And we see the results from the majority, who says A. It would be tempting to say there is no IP because we communicate inside the LAN, and it's true that if we communicate inside the LAN, we don't need an IP address. But if you think about it, if we do not use IP addresses, that means also we can communicate only without the LAN. That means the software should have to be different depending on whether the printer is on the same LAN or not. And systems were like this 20 years ago, but today, of course, we don't want this. So another hidden principle of TCP-IP is you always use IP. There is always an IP packet header when you use TCP-IP. Even if the communication is purely inside a LAN and this IP packet header could have been omitted, but we don't omit it because we never know. Perhaps tomorrow we will move P to another place, and then we would like only to change the destination IP address and not have to change the software. It would have been tempting to say we send to this, but of course, one of the principles is, as usual, the destination address is the final destination address at the IP layer. So we have seen a lot of this last week already. An IP address is the address of an interface. Right? So we will see when we work with routers in the lab. A router has lots of lots of interfaces, so it has multiple IP addresses. That's a bit embarrassing. Sometimes it would be more convenient if there would be one address for one machine, but this is not how IP works. One IP address is the address of an interface. If you have a machine that has multiple interfaces, like a router always has, then you will have multiple IP addresses. Right. Here are the IPv4 addresses. We've started to analyze how they work. So we mentioned that they are made, in fact, of 24 bits. So if I look at this address here, this is what the computer sees. The B here is what I put to say it's a binary string. The X means hexadecimal, and when it is decimal, I put nothing. So if we look at the last 8 bits, for example, we can map that to hexadecimal digits. We will see that zeros give 0, and this string, 0010, is the binary expansion of the number that we usually call 2 in decimal, and also in hexadecimal. So it gives 02. And this blue block here gives 2 in decimal. If you're familiar with that because you had computer engineering courses, it's perfect. If you're not, here are the explanations that I let you discover offline. A case of interest that we will often see is that when all bits are equal to 1, the number is in hexadecimal corresponds to F, and in binary to 15 or 215. Depending on the number of bits here. So that's something we will often see. We've seen already this network. We will zoom now on this router here, and we will look at its routing table. This is showing only the IPv4 addresses of some part of the EPFL, and this router has something special. It's connected to the rest of the world directly, and then it's connected to the 100 subnet of EPFL, which is the backbone of EPFL. And also, on the backbone, there is a direct connection to one subnet here, which is the lemma subnet. The rest of EPFL, it's connected to via the backbone. So if we look at the routing table of this router, we will see that applying the principle of longest prefix match, we can simply have those 4 entries. So what are those 4 entries? An entry in a routing table is a prefix. A prefix we write usually by giving the syntax of an IP address, or part of an IP address, because a prefix can be shorter than an entire IP address, followed by the number of bits of the prefix. So here, for example, /24 means we take the first 24 bits of this string. Now, this string is obviously dotted decimal, so we should interpret it as 3 times 8 bits, which are write it in decimal. 3 times 8 is exactly 24, so this is exactly this string here. This one is a /16, and this one, 0, means the empty string, 0 bit, and the empty string means it matches anything. Any destination address matches this entry. What does it mean? Well, it means that if a packet arrives at this router, has to be forwarded by this router, we analyze the address. For example, if the packet is to the green network here, 128.178.29. something, it matches Which lines does it match? Well, in fact, the 3 lines. It matches the first one, because the first 24 bits are exactly those one. It matches the second line, because the first 16 bits are exactly those one. And it matches the third one, because anything matches the third one. So it matches the 3. We take the most specific one, which means we go to this next hop, and over the interface that corresponds to the next hop, so we go to this in this direction here. So this is a specific routing entry that goes to the green network here. If I have a packet that goes somewhere else inside EPFL, 128.178.156.3, for example, it will not match the first, but it will match the second. Therefore, we'll go to the second entry, which is this backbone router of EPFL. So it will go to the backbone of EPFL here. And if I have a packet that goes to Google, to another address, 37 dot something, for example, it will not match the 2 lines, but it will match the third line, which means it will go to this direction here, which is the connection of this router to our internet service provider, which is called switch in the case of EPFL. So this router has a default route, which says anything that is not EPFL, go to the north. Anything that is EPFL and is not more specific, go to the west. And the specific things, we follow what is written in the table. So that's very typical of how routing tables are made, having default routes at different levels, at the level of EPFL or at the level of the entire world, allows to have short routing tables, which is the primary goal of this story, is to make sure we don't have in every router all the prefixes that exist in the world. In routers that are at the periphery of the network, like we are at EPFL, the routing tables are typically small, a few tens or hundreds of entries, not more. In the routers that are at the core of the internet, the ones that are on the cables that I show on the front page of this presentation, they cannot aggregate very much. They have to know all the different directions. And here, the number of entries that we have is a few hundreds of thousands. We cannot aggregate very much with IPv4. We will see that with IPv6, we can aggregate more. With IPv6, the number of entries is order of a few tens of thousands. We'll see that more when we talk about routing protocols. Right now, we have to know a few things about special addresses. Normal addresses are the ones that are not in this list here. The address 0 is not valid. It is used to signal absence of address. So if for whatever reason, typically in a program, in software, when you have to put an address and you don't know which address it is, you put 0. That means absence of address. So which means also it's an invalid address. You cannot send an IP packet to that destination address here. But it can be used, as we have seen in routing table, to say the default entry, for example. The loopback addresses are also very practical and often used. In practice, we use only this one, 127.0.0.1, even though we can use an entire subnet of, with a prefix of 24 bits. It means this host. It means any packet that is sent with a destination address of this type does not get out of this machine. This is used typically when you are debugging program, or if you're writing a server code and you want to test your server code, you put your client and your server on the same machine and they communicate with this address. And when you move the server code to another machine, the only thing you need to change is the IP destination address, not the code itself. So you can use TCP-IP for inter-process communication using the loopback addresses. And it is used. It's a powerful way to use inter-process communication by using TCP, for example, between programs that are on the same machine. And when in Lab 3, when you will do your own program, will be highly recommended that you start making it on your own machine, because it's considerably more complicated to debug programs that are on different machines. Private addresses are also very frequently used. Most of you probably at home have addresses of this type, 192.168. In the lab, we'll sometimes use also 10.something addresses, and the 172.16 are also used. Those are 4 blocks of IP addresses that are illegal in the public internet. They are private. Private means everybody can use them. That's the opposite of private property. So you can make your own network and give those addresses. You don't have to ask permission to anybody. In principle, you should not do a network where you take the addresses of EPFL or of IBM, for example. If you do that, you're stealing addresses from another company. They might complain about you. So this is, in principle, an attack if you're doing this. Those addresses, they are free for everyone to use. So when you do your private network, you use this. Most of the business addresses are 10-something addresses here. So most companies have internal networks that use private addresses, and they connect to the world through some special mechanisms that are called NATs that we will see in a second. So in principle, this is used only in a private network. You cannot communicate at the IP layer, in principle, with those addresses. We will see that there is a trick to make it possible. A variant of the private addresses are the link local addresses. Link local is a weird terminology. Link means the same as local area network, viewed from IP. So IP views the world as a connection of subnets, which are local area networks, and sometimes IP literature calls it also a link. So a link means local area network, it means layer 2. Link local means it's an address that is local in a local area network only. So you can have multiple local area networks that have the same addresses, and you can interconnect them. There should not be a problem. In practice, what it means is those addresses should never be routed. So if you have a packet to such a destination address, if the destination address is, if the host, the intended host, is not in the same subnet as you, it will not work. So those addresses are made to work inside the same subnetwork only. Now you could ask, why do we have that? If we're in the same subnetwork, we have MAC addresses that allow to communicate. The reason for that is the one we've seen in the quiz a few minutes ago. We still want to use TCP-IP even if we communicate in the same subnet. And this is used when everything else failed, when you did not manage to get a valid address. Normally, if you are even on a single subnet, if you're at home behind your modem, you will get an address of this type. But if for whatever reason things don't work, a DHCP server doesn't work, or you don't have one, or you don't want to have one, then you can use such addresses here. Then there are specific addresses. There is a block of 224 up to 239, which is used for what is called multicast. Multicast is a completely different story. Multicast addresses are very different from other IP addresses in the sense that they are not the address of one interface. They are logical addresses. They are group addresses. So if you send something to a multicast address, then it is up to the destination to decide whether they will receive or not. And you don't know when you send whether someone will receive and who will receive. Those are not the addresses of a normal IP of an interface. Those are logical addresses. And we will see some example of it when we talk of solicited node multicast address. We will talk again about multicast in a few weeks. The idea of multicast at the origin was to replace cable and Hertzian distribution for TV and for radio, where instead of sending a radio program over the air, over a broadcast channel, you send them over the internet using multicast address. So you would have one multicast address for every TV or radio channel. We will see this is used, but not so much as people thought here. One specific address is this one. That's the broadcast address, all bits equal to 1, and it means everybody. But it is a link local address in the sense that broadcasts are never forwarded by routers. Why? Yes? Spam, yes. That would be a very good way to do a denial of service attack against the internet. You send one single broadcast packet and it reaches the entire world. Of course, this is disabled. This is what we see when we analyze an IP packet. We've seen some of it in the Wireshark traces we've done. The interesting thing for today is the protocol. So one important thing that an IP packet header contains is, of course, the source address and destination address, and a field that is called protocol. When people say just protocol, it usually means this field in the IP packet header, and it means what is contained inside the payload, typically TCP or UDP. Those are the two standard cases. So the most frequent cases are the packet contains TCP or UDP. A special case also is ICMP. ICMP stands for Internet Control Messaging Protocol. It is the error messages of the IP layer. So if you send a packet to somebody and that somebody does not exist, perhaps a router will complain and say, oh, that thing doesn't exist. And that complaint message, this error message, if it is supported by routers, is sent using a packet that is formatted according to ICMP. It's called the ICMP protocol. We will see also a bit later that there is a TTL. This field here, we'll see that next week, what it says. We can do almost verbatim the same for IPv6. What we have mentioned last week is that IPv6 addresses are much larger, 4 times larger, which means the state space is raised to the power 4. And this number is believed to be so astronomically large that there's probably quite a long time until we will need anything else. But as I mentioned before, the bad news is IPv6 is not an extension of IPv4, which is what you would like. It's like what Apple does when they change the processor. The programs that work with the old one don't work with the new. It's the same with IPv4 and IPv6. So if you have, for example, a machine that wants to talk to some IPv6 servers or some IPv4 servers, so there are, and there will be in the world, machines that have only IPv6 and machines that have only IPv4. Now, if you get a new address today, it's probably an IPv6 address. But there are lots of places in the world, especially in the old world, in the places of the world that had IP addresses before the IPv4 addresses were exhausted. They are exhausted now, so you will not receive new blocks of addresses. So old machines are running IPv4. And since it's a pain to move from IPv4 to IPv6, there is no incentive to move unless you really are hitting problems. So a lot of EPFL, for example, is still running today on IPv4. Things like InfoScience, if you go to the library of IEEE, they they verify that you are at EPFL by checking your IPv4 address. So if you go there with IPv6, they will ignore you, so it won't work. So there are lots of lazy things like this that are being done in the world, especially in the parts of the world where there had been IPv4 addresses for a long time. So there are machines that work with IPv4 only. There are also machines that work with IPv6 only. If your smartphone is on an IPv6 network where the cellular network has only IPv6 addresses, you will have only IPv6 addresses. And then the problem will be, what do you do if you want to talk with something that runs IPv4 and IPv6? We will see that you need to do some trick because in their wisdom, the people who standardized the internet, they thought we don't want to handle that case. Right? So we will see that there are a few tricks we need to do. One of the tricks is that most machines today have both IPv6 and IPv4. So you can try on your machine, whether a Mac or Windows or Linux PC. In the lab, we have seen how to enable or disable IPv6. So your machine typically has both, except if it's a very, very old machine, but it's probably unsecure and you should patch it and make it more up to date. And then you will have both IPv4 and IPv6 because IPv4 or IPv6 is just software. It's just a software change. So if you maintain your operating system, you have both. And the ideology, the theory of the internet is we use what we call dual stack. So if an application speaks to a machine that is IPv6 only, it will send IPv6 packets, and hopefully there is an IPv6 internet between the two. If it speaks to a machine that does only IPv4, it will use IPv4 packets. There is IPv4 and IPv6, so there are two different network layers, but TCP and the MAC layer and the application layer are in principle the same. So there is not TCP-V4 and TCP-V6, they are the same in principle, but in practice they are not. Because when you write a program, when you send a packet to a machine B, you have to say to which address you send it. So you have to put the address in the code. If your code works only for IPv4, you can never send a TCP segment to an IPv6 machines. Right? So the protocol itself is the same, but the code that implements the protocol at some point will need to handle IP packets and things like addresses. Here is the same routing table at the same machine that we've seen before, but in IPv6. So IPv4 and IPv6 are two separate things. So a router, like a host, typically has both an IPv4 interface and an IPv6 interface, and both an IPv4 routing table and an IPv6 routing table. The two routing tables may be completely separate. They are not derived one from the other. Here are, for example, what we would see at EPFL. We would see the same things as before, except it's more complicated. With IPv6, everything is very long, much harder to read. That's one of the reasons people don't like it and stay with IPv4 if they can. It's much easier to say /24 than /56 or 64. Although, using hexadecimal digits, the mapping is easier, but everything is very, very long. So here, for example, we also have the default entry. That means nothing, 0. And this is the name of the next hop or of the interface. I'll come back to it in a second. And this is the prefix of the rest of EPFL, 2001-626-18. That's the EPFL prefix. And it is 3 blocks of 16 bits each, so it's 48 bits long. And this is a specific subnet of EPFL, a specific IPv6 subnet of EPFL, the 1A4, which is this subnet here, which when the prefix here is 64. So very often, not always, with IPv6 you can do whatever you want, but very often the network prefix, the network mask is 64 bits with IPv6. It's not mandatory, but it's what is very often done. So that's what we see here. Then we see that the next hop is given in the form of an IP address. In the previous slide, I also showed an IP address, but here, those IP addresses are special addresses that we will cover in a minute. Those are link local addresses. Those are addresses that are valid only inside the link. And since there are multiple links at this router, at least 2, you also put on which of the links. So that means you go out on interface number 1, and here you go out on interface number 2. This is the Windows notation. In Linux, you would have things like ETH0 or ETH1. Because the IPv6 addresses are very long, there are special rules that we need to learn on how to write and decode them. First, they are written using hexadecimal digits. So here is 2 addresses. This one is a public one. If it starts by 2 or 3, it's a public address. If it starts by FD or FC, it's a private address. Like we have seen in the IPv4, an address that starts by 10 dot something is a private address. In IPv6, we can do the same. With the difference now that the address space is so large that typically what you do with IPv6, if you use private IP addresses, you will try to give the same structure to your addresses as your public IP addresses. One of the problems with the private IP addresses is that in the real world of companies, one thing that companies do all the time is to reorganize themselves. Right? So they are sold, bought, merged, split. So you had a nice network organization with IP addresses, 10 dot something, and then you merge with another company that is also using 10 dot something. So you have complete chaos because you have to do a renumbering of everything. And with IPv4, you have to do the renumbering. With IPv6, what people try to do is to have a private prefix for every company. So here, this is one of the prefixes of EPFL, the one we use in the Smart Grid project. There are other prefixes because there are other projects of EPFL that have required a private address space, so that we have different address spaces. And if the address space is so large that one of the things we do is we give the same numbering plan to the part that is outside this prefix, so that if we merge, if a machine that has this address would become public, the only thing that would change is we change the private prefix by the public prefix. If we do things smartly, this is possible. That's the kind of things that are made possible by having a very large address space. Here are the rules for how to write the IP addresses. We write them by pieces of 16 bits. 16 bits means 4 hexadecimal digits. So here's, for example, an IPv4 address. One of the ones we use in the lab, for example. IPv6 address, sorry. So there are 8 blocks of 16 bits here. Now, there are lots of zeros. We can remove the zeros by using 2 rules. First, inside a piece, the leading zeros can be omitted. For example, here, there is 0620, we can write it at 620. So it doesn't mean there is a block of 3 digits only. Every block is always exactly 4 digits. If there are missing digits, it means you put leading zeros, like you do when you write a number using hexadecimal or decimal representation. Right? And the second thing is we put columns between the pieces, and an empty column means, an empty piece means a double column, means as many zeros as is required. For example, here, this block of 4 pieces all equal to 0 can be replaced by an empty string. So this is how we can encode this here, by removing all the zeros. And similarly here, the leading 0 of this is removed. So this is how we can have compressed addresses that are nicer to write, if there are lots of zeros. Of course, this syntax could be ambiguous if there would be multiple blocks. If there are 2 blocks of as many zeros as required, you don't know how many zeros there is in every block. You just know the total number of zeros, the total number of empty blocks. So the rule is this is allowed only once in an IPv6 address. If you see 2 of those blocks, it's an illegal writing. Here are some examples of what are called global unicast address. So the IETF has decided that the blocks that start with 2 and 3, so we can write this as the block 2000/3. So 2000/3 means the prefix that starts with 2000 hexadecimal digits, and /3 means the first 3 bits. The first 3 bits of that. So what are the first 3 bits? Well, the first 3 bits are the first 3 bits of the first hexadecimal digit. The first hexadecimal digit is 2. In base 2, when you write 2, it gives 0010. So the first 3 bits means 001. So the 2 hexadecimal digits that have those first 3 bits are 0010 and 0011, which are 2 and 3. Right? So 2000/3 means the same as this. It means any IPv6 address that starts with a 2 or a 3. And this is allowed today for normal IPv6 addresses. So you see that the IETF is very wise and is considering that all addresses we allocate today are in this block. Perhaps in 100 years we will need a new addressing plan, then we will use perhaps the 4 and 5. Here are some of the addresses. You recognize the EPFL address here. Switch is the internet service provider that serves EPFL, and what you see is that the EPFL addresses are in fact a sub-prefix of switch, which was not at all the case for IPv4. For IPv4, for example, EPFL is 128.178 something. ETH, which is also served by switch, is 129.132, which is not in the same block, so that switch has multiple blocks of IPv4 addresses. In IPv6, we don't have that. Switch has only 1 block, and all the customers of switch are sub-blocks of this. What is the advantage? You can skip a lot of DNS routing, although I would not call that DNS routing. DNS has to do with names. This has nothing to do with names, it's just addresses. But the routing tables in the routers that are in the backbone of the internet can be compressed. Today, a router that is in the backbone of the internet, somewhere in New York City, for example, has 1 line for EPFL, 128.178/15, has also 1 line for ETH, has 1 line for University of Bern, etc. It has probably 100 lines for all the customers that are served by switch. Whereas for IPv4, for IPv6, it has only 1 line, which is the 2001/620. So this is how with IPv6 we can compress more. Question?
So that means that in the event that EPFL shows another IP provider, then we have to renumber.
Exactly. The question is, does it mean we have to renumber if we change the internet service provider? Yes, we may have to renumber. Question?
Yes, I was wondering, like this router in New York, are all these entries say that you broadcast routes.
So the question is, this router in New York City, do we route manually the entry? What do you think?
Well, I hope it's not manual.
No. The internet would not work if it would be manual, right? As I said, there's hundreds of thousands of routes, and somebody of EPFL or somebody, EPFL would need to pay somebody, a little monkey, in New York City, in all the places in the world to do this monkey job. Of course, there is what is called a routing protocol. So the topics will be OSPF and BGP. Those are the two examples we will see and do in the lab, how this is automatically done without having to do it manually. You still need to run this routing protocol. We will see it's non-trivial, but this is done. This is the job of BGP and OSPF to do that. There was another question?
If we just have one line in the New York router for switch, doesn't that just move the other lines that we had before for IPv4 to the switch router?
No, because this, I mean, with IPv4, what happens is that the block that corresponds to EPFL has nothing to do with the block that corresponds to ETH. So 128, 179, and 178 are EPFL, but 128, 177 is, I don't know where, perhaps it's a network in South Africa. And 128, 176 is perhaps a network in Latin America. So there is no way to aggregate the things together because they go to different directions. If we would like to do that, we would need to renumber, but the problem is those addresses are, it's possible to renumber if all addresses would be allocated to switch already, but they are not. Those addresses that we would need to make the blocks contiguous, they are allocated to other parties in the world that have their own addresses. They won't give it to us. Plus IPv4 addresses today are very precious. They have very high value because you can't buy anymore any IPv4 address. So if you have one, you keep it. As for IPv4, there are special addresses. More, in fact. Empty string means absence of address. The loopback address is the 1, so as many zeros as everywhere, and the last bit equal to 1. It means this host. The local addresses, like the 10 dot something, are the ones that start with FC00/7, so FC something or FD something. So F and C are the hexadecimal digits. And similarly to the link local addresses, there are the FE80, the first 10 bits of this, so FE, and then the first same 2 bits as the bits of 8. Now the difference between IPv4 and IPv6 is that the link local addresses in IPv4 are used when nothing else works, so in principle you don't use them. But in IPv6 we use them all the time. So whenever communication is between two hosts that don't need to go through routers, they can, and often they will, use link local addresses. We will see that, in fact, one of the things that an IPv6 host does when it boots is it creates first a link local address that allows it to communicate with other systems on the same local area network. And then it will speak to routers or to DHCP servers to get its prefix. But the first thing it will do is get its link local address. Because of that, some people think that in the very long term, we could do without MAC addresses, because with IPv6, we can communicate at the local level with IP addresses here. So in a remote world where IPv4 is completely extinct, and my prediction is true, my prediction is that IPv6 is the final version, then we can cast IPv6 in hardware. And then you could give IPv6 addresses and communicate without MAC addresses. But I will be probably dead before that happens. Multicast addresses are the ones that start with FF, so they're very easy to recognize. And there is one special that we will see in a minute. For example, link local broadcasts, which was in IPv4 all bits equal to 1. Here is this one, FF02, then lots of zeros and 1 at the end. And then with IPv6, you can do funny things like all link local routers. So that means if I send a packet to this address, every system that thinks it is a router will receive the packet. So that's a way to speak to routers, for example, when a machine is booting and is trying to discover who are the routers around in order to make its own default gateway. The IPv6 packet header is essentially the same as IPv4, but all details are a bit different. They are called differently. Something is different, it's the length, because now every IPv6 address is 128 bytes. There are 128 bits. There are 16 bytes for a source address and 16 bytes for a destination address. So there are 32 bytes of address in every IPv6 packet. Right? Sometimes it's an issue. It means if you want to send 1 bit of information with IP, with TCP-IP, you need 40 bytes of IPv6 header. And we will see that there are also 20 bytes of of TCP header. So you need 60 bytes that are not carrying any useful information. Plus, we will see there are other things for security, for example. An annoying thing with IPv6 is that everything has been renamed. IPv4 was done at the end of the 70s, and since then, people find that the terminology adopted in IPv4 is a bit obsolete, so they've changed the naming. Unfortunately, what happens is everybody keeps using the IPv4 names, even in the context of IPv6, even if they are different. One example is the protocol type. Protocol type is called next header. Now, it is called next header and not protocol because it means, well, the next thing that is inside the packet. The idea of protocol type is normally inside an IP packet, you have a TCP segment or a UDP segment. But we will see that there are lots of cases where you do weird things, like inside an IP packet, you can put an IP packet in turn, for example. That's one of the ways you can solve the problem of communicating to IPv4 when you have only IPv6. You can put an IPv4 packet into an IPv6 packet. Also, you can use headers that are used for encryption and authentication, so security headers. So the name is called here next header. Apart from that, it is exactly the same as the protocol type here. Sometimes we need to map IPv4 addresses to IPv6 addresses. So we need sometimes to have the different notation for the same string. So for example, if I want to say this string that is perhaps extracted from an IPv6 address, if I write it in IPv4 address, which is the notation I would have? That's the kind of things we do at EPFL, for example, because the EPFL system managers of the network, they are smart, they are Swiss, so they want a well-organized numbering plan. So the IPv6 address of a machine is exactly the same, or contains exactly the IPv4 address. So the machine 128.178.15.8, you translate that into hexadecimal digits, and you put it somewhere into the IPv6 address, so that you are sure when you talk to one address, to one machine, you cannot make any confusion. So let me open the poll here. The correct answer is B. Voilà, we do a break.